I have. Yeah. All right. I thought we did this one yesterday.
No, that was the one with the two people in the car.
Oh. Okay. Oh, this isn't it. Sorry. Particles moving in the xy plane, constant acceleration, and the velocity of this, and is at the origin. So that whole first part is telling you the initial conditions. And then at 2.6 seconds, the particle velocity is this. Find the acceleration particle at any time. All right. So we know, I'm just going to kind of arrange this in my mind. At t equals 0, v equals 3i minus 2j, and s equals 0i plus 0j, and a is constant. They don't tell me what though, right? And then at t equals 2.7 seconds, v now is 9.20i plus 8.40j, and we don't know what s is or anything like that. Find the acceleration of the particle. So we know it's a constant acceleration, so we can use that a, the definition of a, which is delta v over delta t. Since it's a constant, we can do the deltas rather than having to do the derivative. And so, of course, that is v final minus v initial over delta t. And so we're going to end up with an a of, let's see, negative 3i, because that's 0 minus 3. Sorry, I'm doing the wrong thing. V final minus V initial. So for the V final minus V initial in the I, I'm having 9.2 minus 3I plus 8.4 plus 2J all over a time of 2.7 seconds. And I should have had units in the upper part there also. So I get, let's see, 9.2 minus 3 divided by 2.7. I get A, vector A is 2.30I, and I can do each part separately, plus 3.85J. That's my acceleration vector. Why don't I'll cast this out as a window. I forgot about that, sorry. All right, so that's my acceleration, and it's constant, so no time-dependent variables in there. Nice. Find the coordinates at time t. So now from this, I'm going to I need to do the antiderivative to get back up to my position location. So I'm going to do The antiderivative of A is B, and that will be 2.30 t in the I direction, 2.30 plus the initial x in the I direction plus 3.85 t plus the initial y in the j direction. It told me, though, what I could use for those v initials, because it told me my velocity at time 0 was 3, -2, right? So I can rewrite this. This is 3, and this is -2. So I end up with that this is 2.30 t plus 3. This should all be meters per second, by the way, plus 3.85 t minus 2 j. Good thus far with that? Okay. And then I'm going to take the antiderivative again and get my position vector. And nicely in this one, it told me it started at the origin. So the initial starting conditions are 0. So I'm just going to leave those off and save myself a step. But I'm going to have 2.30 over 2 t squared plus 3 t in the I direction plus 3.85 over 2 t squared minus 2 t in the j direction. And remember, I would bring constants in there, but I already know the constants are 0, so I'm not going to bother with them. Substituting, and so there, I would probably clean up a little bit before I actually put it into WebSign, but that should be your answer there. So. All right, so basketball player who is 2 meters tall is standing on the floor 8 meters from the basket, as shown in the figure. Shoots the ball at an angle 38 degrees horizontal. At what initial speed must he throw it so it goes through the hoop without striking the backboard? The basket height is 3.05 meters. All right, so I want to be able to do this separately, so I'm going to start off breaking up my initial velocity. So this is going to be v, and so this tells me this is 38 degrees here. So v sine 38 degrees and v cosine 38 degrees. So really what I'm saying is the vector v is v sine, oops, one way to look at it, it is v cosine 38 degrees I plus, this is the initial, by the way, plus vi sine 38 degrees j. That's my initial condition. My initial position, s, the vector s, let's call that, we'll say that it is at 0, I plus 2j. That's my initial position. My final position I want to get to is at 8I plus 3.05j. Right? Your final x component is going to be different than this one. You know, it's cast up on the screen also, back where you were if you want. This is better. That's perfectly okay. And so we can do these separately. We know that our acceleration in all of these is 0I minus 9.8 j. That's our acceleration vector in these cases. So my displacement vector is going to be 8I plus 1.05 j. That's my displacement vector. So all this being said, I know that horizontally and vertically it has to be at the same place at the same time, right? And since I have a constant acceleration, I can use my equations of constant motion, right? And I think just for clarity, I'm going to break it into separate I's and J's, all right? Rather than doing it together. I think it'll be less confusing if we separate it. Yes? No? So let's go right down the middle, X and Y. The only common thing here is time. And time is in common. So in the X direction, my delta S is 8. My V is VI cosine 38 degrees. My acceleration, of course, is 0. So I'm going to have that I'm going to use X equals X naught plus VXT plus 1/2 AXT squared. And I'm going to have 8 meters equals VI cosine 38 degrees at time t. On the y side here, my delta S is 1.05 meters. My velocity is VI, my initial velocity, sorry, VI sine 38 degrees. My acceleration, of course, is negative 9.80 meters per second squared. And putting that in. Now, the other way to look at it is rather than looking at the delta X, I could look at X and X naught, right? I could put them in either way. So I'm going to use, let's use this form, delta Y equals VY T plus 1/2 AY T squared. And so I'm looking at my 1.05 meters equals my VI sine 38 T plus 1/2 minus 9.80 meters per second squared T squared. Nice is that the T is common, and so I can remove the T by, like we did the other day, solving one side for T and then substituting it into the other. So bring these together now. And I have that I'm going to do 8 meters over VI cosine 38 degrees equals T. And then I'll bring that and substitute it in over here. And that's where my calculator is my friend to be able to solve what ends up being a little bit of looking nasty, because you end up with 1.05 meters equals, and the VI sine 38 multiplied by the 8 meters over VI cosine 38 degrees, because I'm substituting in for that T, right? And we'll do minus 9.80 O meters per second squared times 8 meters squared over 2 times VI cosine 38 degrees quantity squared. Now, some nice things happen, like the VI drops out here, and you're left with tan of 38 times 8, right? But it's then you can just rearrange and solve for VI. You can do the algebra. I would use the calculator, though, for ease. Maybe simplify it one more step down, and then put it in your calculator and give it a try. Use the solver. All right? So give that a try. See what you come up with, and I'll see what I come up with. So, the range equation on special condition of this with this be at theta. You know that the displacement in the y is 0, and the displacement in the x we call the range of the projectile. And so in the y, using our basic kinematic equation, right, that we use a lot, we have 0 equals v initial sine theta t minus 1/2 g t squared. This is in the y direction. In the x direction, we have what we'll call the range, which we'll call x equals v initial cosine theta t. And what I want to solve for is x. So I'm going to say that t here equals x over vi cosine theta. Substituting that in, bringing those two together, like we kind of like what we did last time. We have 0 equals vi sine theta times x over vi cosine theta minus g over 2 minus, x squared over vi squared cosine squared theta. Substituting that in, right? Then I can divide both sides by x and get rid of one of the x's, right? And I could also get rid of a cosine because I have a VI. Well, these VI's disappear. I get rid of an x, right? I'm going to get rid of a cosine. So after all of that, I'm left with 0 equals sine theta minus gx over 2 pi squared cosine theta. Rearranging that, getting x by itself, I have gx 2vi squared cosine theta equals sine of theta. So I end up with x equals 2 vi squared sine theta cosine theta all over g. And so for a projectile launched at any initial velocity at any angle on any planet, that will be the range. I don't know how you guys are with your trig identities, but 2 sine theta cosine theta is an identity. And so this can be simplified to x equals pi squared sine of 2 theta all over g. That's normally how it's given. Those are the same thing. You have the trig identity of sine of 2 theta equals 2 times sine theta cosine theta.